remember I needed to record today. So we're talking about nuclear fission today and nuclear fusion. Nuclear fission is when a nucleus of an atom splits into two smaller elements. And this is the chemistry that happens in nuclear bombs, but I also want to mention this also happens in nuclear power, and we're going to be talking about both today. And so, just like last week, we were talking about alpha and beta and gamma decay, right? And we were talking about how all of those happen in radioactive elements, in elements that already have a nucleus that is unstable for some reason. The same applies for fission and fusion. Not all elements can undergo fission. All of them can undergo fusion, but yeah. So when we talked about chemical bonding, everything wanting to be stable as far as its electrons, so they can gain or lose or share electrons to become chemically stable, that is not how they become stable in their nucleus. And if you remember on Friday, we learned that like oftentimes if it's too many or too few neutrons in the nucleus, that makes that nucleus itself unstable. And in nuclear reactions, they happen because of that instability, and they happen when they feel like it. And so a type of nuclear reaction is nuclear fission. And we're going to talk about how we can sort of encourage that to happen, but only in an element that is capable of undergoing fission. I don't know if I quite answered your question. But basically, this is the nucleus, this isn't electrons, and so it's sort of a different world. And so in nuclear fission, this is one example. Uranium-235, by the way, undergoes nuclear fission. And if you look at the periodic table, is uranium-235 the most common version of uranium? What's the most common version of uranium? 238. And so only uranium-235 undergoes fission, not uranium-238. So only the least common version. But if you have uranium-235, what we have found is if you bump it with a neutron, if you shoot a neutron into it, for a really, really, really small split second, that neutron becomes incorporated in the nucleus, and then the nucleus is like, whoa, whoa, we are unstable, and it splits apart. And so adding that extra neutron puts it over the edge, basically. And so it splits into two smaller elements. And when fission happens, and I'm not quite sure why, but what all the writing says is that when fission happens, it makes two smaller elements and 3 single neutrons are released. And what do you think those single neutrons can do? Go do it again, hit another element, and essentially, yes, a very quick chain reaction kind of appears. And so in this example, they're showing uranium-235 temporarily being uranium-236 because that neutron hits the nucleus, and then it's like, no, I'm unstable, and it splits apart into 2 elements. Do you think these are the only 2 elements it could split into? No, there's actually 50 pairs of elements that form when uranium-235 splits, because it doesn't always split with the exact same number of protons, right? Splitting each time. And so there's different combinations. But let's talk about the history a little bit and how they figured it out. You don't need to write any of the history down. So in 1932, James Chadwick discovered the neutron. And he did that because he was shooting alpha particles at beryllium-9. And he, once he discovered that neutron, he then tried to fire neutrons at different elements. And he was hoping the neutrons would become part of the nucleus and maybe make another element. That's what he was hoping for. However, he kept shooting those neutrons at elements. He kept slamming them in, expecting them to join that nucleus. And it never happened. They weren't able to become part of that element he was shooting at. And he wanted to figure out why. And by the way, you're going to notice a lot of these names are familiar because they've all have elements named after them now because of the work that they've done. Nuclear chemists got a lot of credit on the periodic table. So fermium, Enrico Fermi, an Italian physicist, was working in his villa in Rome, and he solved the problem of why the neutrons were not actually entering the nuclei of the atom. The neutrons were going too fast. Basically, they were hitting the atom and bouncing off of it. And so what he did is he did the same experiment, but he was shooting the neutrons underwater. And by using water to slow the neutrons down, he was able to get them to actually enter the nuclei of the atom for the first time, and hence change the nature of the nucleus and history. So His next experiment, or his important one, right, was that he was trying to bombard uranium with slow neutrons, again, trying to form a new element. And what he was attempting to do was take uranium-238, throw a neutron at it, and he was hoping to get neptunium-239. He wanted that neutron to kind of change itself into a proton when it got there. And so he was hoping for neptunium-239 and maybe beta decay as well, because he'd add that neutron. He wanted that neutron to undergo beta decay. But neptunium-239 did not form. He was not able to detect it despite many experiments. However, under close analysis, he noticed that there was a very small amount of krypton-92 and barium-141. And if you add up the number of protons in krypton and barium, it's equal to the number of protons in uranium. So he said, somehow by throwing in those nuclei, I didn't cause beta decay to occur, which is something they were familiar with. I caused two smaller elements to have formed. It's like uranium broke apart. And so the explanation for that, though, came from Lisa Meitner. Element 109 was named after her. And she was doing research with neutrons as well. And she said the barium must have happened from the splitting of the uranium atoms into two fragments, and you had two elements left over. And she came up with the term fission, which is why we named an element after her. Now, they only saw it in really tiny amounts, though, and they needed an explanation for why it was so tiny. And we know that there's two versions of uranium that occur naturally. Uranium-238 is found 99.3% of the time. Almost all uranium is uranium-238. So that's what they were working with. Uranium-235 is only 0.7% of all the uranium out there. And that's why they saw really tiny amounts of those smaller elements, because only uranium-235 can undergo fission. Only uranium-235 splits when a neutron hits it. And so that became really important for both our nuclear power and our nuclear weapons. Uranium-235 is the element that we use in nuclear power and in nuclear weapons, but it's only 0.7% of all the uranium out there. And so it's a political issue, but the UN, is it the UN that controls who has access to like the technology for isolating uranium-235? I believe it is. And certain countries are not given that information and technology due to unstable governments and things like that. So they control the knowledge. Obviously, humans figured it out, right? And then they can kind of control which countries have access to that technology and knowledge for isolating uranium-235. So again, you don't have to write this down, but it is important that you're watching and paying attention. I see a lot of people on cell phones, which really isn't school appropriate. So we're going to talk specifically here. What? We're going to talk specifically here about the fission of uranium-235.
We're good.
All right. So uranium-235 undergoes fission when a neutron hits it. And what happens is for 0.00000000000001 seconds, it's uranium-236. And then that is just unstable. And so that element splits into two smaller elements. I know this is in yellow, but you don't have to write this down. But basically, it can be any combination of elements that add up to 92, right? Because uranium has 92 protons. So it can be any combination of two elements that adds up to 92. It also releases 3 neutrons. And what I haven't mentioned yet is it releases energy as well. So for every 1 uranium-235, 3 neutrons are released and shot out. Each neutron can then go hit, if you have them isolated, if you have a bunch of 235 together, each neutron can just shoot out to a nearby uranium-235 and cause that one to undergo fission. And so a whole bunch of them can go at once, and we call that, as someone already said, a chain reaction. I do want you to write this last bullet point down. It says if the amount of uranium-235 is sufficient, in other words, if you have met critical mass, then the number of neutrons generated is high enough to result in a nuclear explosion. We're going to talk about nuclear power today. We're also going to talk about nuclear weapons very basically. Can I move on? All right. So here's my little neutron right here. I like this visual. I stole this PowerPoint from someone else for this visual. And so the neutron hits that uranium-235. It splits into two smaller elements. It releases 3 neutrons. Those neutrons hit those 3 uranium-235s. They each split into 2 smaller elements, release their own, and eventually we get the explosion. Okay, what? So, because of the amount of energy that's being released at the same time. And so this reaction happens really quickly, 10 to the negative 14 seconds for that reaction to happen. So it can spread very quickly, but eventually it releases so much energy that it explodes outward. So when they make a nuclear weapon, first of all, you need the technology to separate uranium-235 from uranium-238, because in those initial experiments, they were shooting those neutrons and just finding trace amounts of other elements, because mostly they were hitting uranium-238s, which wasn't impacted at all. So you need to separate your uranium-235 from uranium-238. And then you just wrote down about critical mass, right? You need to have critical mass to have a nuclear explosion. To have enough heat and energy released from the speed of that chain reaction, you need to be at critical mass. Well, let's think about a nuclear weapon for a second. You have to deliver it where you want to use it. You don't want it getting accidentally detonated beforehand, right? So the way the technology works in a nuclear weapon is they have 2 basically chunks or pieces of uranium-235 that are not critical mass on their own. So if one started going or the other one started going, it wouldn't be enough to have an accidental explosion. And what happens inside the weapon itself is they have a detonator that slams those 2 pieces together, and those 2 pieces combined reach critical mass. And so then you can basically have that chain reaction start happening. And so what happens in a nuclear weapon is probably somewhere in the center, that detonator slams them together and it starts going, lots and lots and lots. Chain reaction builds really fast over a short period of time. And eventually it releases so much heat and energy that it explodes outward. Now, before the explosion, do you think that every uranium-235 will have undergone fission? Do you think every single one will have split? Probably not. So when a nuclear weapon releases, it releases some uranium-235. What else does it release out into the world around it? Well, radiation from uranium-235 and from what else? All the elements that were made, right? Remember, there's 50 different combinations of what elements are formed when each uranium splits. And chances are that some of those elements that are formed are stable. Chances are also good that some of those elements that are formed are radioactive. And so we talked on Friday about how there's radioactive elements in the world around us. We know we receive radiation regularly anyway. But do you think it'd be safe to say, or dangerous to say, true to say, that in an area where nuclear weapon release, that there are higher levels of radioactivity than in a normal place, right? Because they've taken uranium-235 from everywhere and they've collected it, and then we've released it over the area where the bomb exploded. And so yes, uranium-235 is out there, and all the elements that uranium broke into that are radioactive are there as well. And so what happens is an area where a nuclear bomb has been used has an increased higher level of radioactive elements than it otherwise would have. because they've been exploded all over it. And with that comes radiation. And we're going to talk about half-lives later this week and how long that radioactive elements can persist. But the idea is that you take a world that already is a baseline of radioactivity, and we've sort of put extra radiation there. And in areas where there's been nuclear fallout from weapons, they do see higher levels of certain types of cancers, like thyroid cancers, blood cancers, tumors of other sorts, birth defects in babies born afterwards. And so we know that there is a negative environmental impact from having these nuclear weapons explode. Questions so far? We also use nuclear fusion. Okay, yeah, go ahead, Kai. I'm not really sure what that refers to. But I'm also not an expert on this topic. Do you know what nuclear winter is?
Radioactive.
Like a season that's radioactive?
Yeah, I guess so.
I don't know. I'm not sure. I'm not familiar with that term. So nuclear fission is also what we use in nuclear reactors for energy. And there are nuclear reactors in our world. You guys in 2 different documentaries you've seen have seen some stories of failed nuclear reactors. But I want to point out that there's over 400 on Earth right now, and over 100 functioning nuclear reactors, I believe, in the United States. And so nuclear power is a thing, and it is something that we rely on. And it actually has a lot of benefits. Think about it like this. So to make a nuclear reactor like a weapon, we need to collect radioactive material, right? And we do need to concentrate it. But if we didn't collect it, where would it be? Out in the world doing its thing anyway, right? And so a pro or an argument for nuclear power is that you're taking this radioactive material that would be decaying and releasing radiation into our world anyway, and we're using it for our benefit, okay? And basically what happens is they make nuclear rods of radioactive material, and they put them underwater and to moderate the neutrons, and they shoot neutrons at it, and they have fission occur. And what happens is because it's underwater, it heats the water, and that water produces steam, and the steam spins turbines, and we make electricity that way. And so a positive for it, or an argument for nuclear power, is, well, this radioactive stuff is going to be undergoing radioactive decay anyway, we might as well benefit from it. When they make those nuclear rods, they are much smaller than what you would need for critical mass. So they are never going to turn into an accidental bomb and explode. There's not enough material for them to do that. So that is one safety feature that they have going for them. In order to have a nuclear reactor, you do need it to be near water, because like I said, you need that water to produce the steam. And they also use cool water to cool it down. In my environmental science class, I was actually just talking about manatee populations in Florida, and there's a nuclear reactor in Florida. And they have now found that over 2/3 of the wild manatees prefer the water outside the nuclear power plants than they do the natural warming springs. And their populations have actually grown because they have such a consistent source of warm water, and that's what they need to be healthy. And they're talking about shutting down one of those nuclear power plants, and it's a real wildlife issue of what's going to happen to all those manatees. There isn't enough warm water sources in the region where they live to support all the manatees if the nuclear power shut down. So that's an interesting one where you don't usually think of them having an environmental impact that's positive, but that's an example of one. One of the biggest challenges of nuclear power is what to do with the waste material once those nuclear rods are mostly used, kind of like in the weapon. Do you think that they are 100% used? Do you think every radioactive element has done its thing? Probably not. So it has to be treated like dangerous radioactive waste. And so we learned on Friday about how in order to protect yourself from gamma radiation, you need thick concrete. And by thick, I don't know if I defined it, it's usually at least 10 feet thick of concrete. So to dispose of nuclear waste, one thing that's been done is they'll often put it in barrels, and they'll dig a big hole, and they'll put 10 feet thick of concrete, and then they'll put the barrels in, and then they'll cover it up with 10 feet thick of concrete, which could work, but concrete can crack, right? Earthquakes can happen, or the concrete can fail. And then if the barrels are also leaking, it can leak into the environment, get into water sources, and be a problem. Anyone heard of the Hanford's nuclear site upriver, up along the Columbia? That's in Washington, and it's a site that they're spending millions and millions of dollars cleaning up leaked radioactive material from the Hanford nuclear plant. And some of that nuclear material has leaked into the Columbia River and flown out to the ocean and gone out to the ocean. So it's gone past where we live, right? And so the biggest challenge with nuclear power is actually disposal of waste and in a safe way, because now we've taken stuff and concentrated it, and we don't want that concentrated material to leak in a certain area and cause problems. So I said that nuclear fission, nuclear bombs, right, have a whole lot more energy than other types of explosives. Anyone know where the energy comes from? Why is it so much energy? Why do we want to use it for our electricity? It's so efficient. The amount of energy you can get from some atoms compared to burning coal or something like that is just extraordinary. And the way it comes from is an equation that you may have seen before. Have you seen this equation? Whose is it? Einstein's. I do want you to write it down and know what it stands for. Einstein's equation, E equals mc squared. E stands for energy. We're not going to actually calculate with it, but if we were, the unit we would use is joules. M stands for mass in kilograms. C stands for the speed of light. And then I just wrote the value. The speed of light is a 3 with 8 zeros. So what is this equation she's talking about? Energy, mass, speed of light. So when nuclear reactions occur, when nuclear decay happens, and we get that gamma radiation in particular, that is, remember I told you it's a really high energy, and I never really mentioned where the energy came from? The energy comes from the fact that matter is converted into energy. Matter is literally destroyed. In regular chemical reactions, we're just making and breaking bonds, connections. In nuclear chemistry, matter is destroyed. It's literally transformed from a physical material that has mass that you can weigh, and it is destroyed and formed into energy. It's kind of confusing and mind-blowing, but it's a huge amount of energy. So this equation says mass, which is the mass of the matter that is destroyed, times the speed of light squared is how much energy you get. And so when there's nuclear reaction, you literally, especially when there's a lot of atoms doing it at once, you literally, it'll weigh less afterwards, even though it's broken into things, because some is destroyed. Yeah.
Isn't matter not able to be destroyed electrically?
Except in nuclear chemistry, except in nuclear reactions. And so that's why it's such an energetic reaction. So the last topic for today is nuclear fusion, which is, you need to know the difference between fission, which is what we just talked about when it splits, and fusion, which is when things fuse and come together and make something bigger. So in nuclear fusion, nuclei combine to form something bigger. It makes a bigger atom than it had before. And the best example of nuclear fusion is our sun or any kind of star. Before stars are born, they start off as just clouds of hydrogen, and they collect more and more clouds of hydrogen and build more and more of a gravitational pull until those hydrogens are eventually so attracted to each other and that gravitational pull that they're zipping around really, 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 really fast. And we say in Earth science that a star is born when it reaches 40,000 degrees Fahrenheit and nuclear fusion begins. Or is it 10,000 degrees Fahrenheit? It might be 10,000 degrees Fahrenheit. Haven't taught Earth science in a while. It's a really hot temperature. And so in nuclear fusion, what happens, and we have already touched on this when you watch the Wonders of the Universe quiz, but in nuclear fusion, basically 4 hydrogen nuclei, which is just 4 protons, right, slam into each other. And if they slam into each other and stick and it releases 2 beta particles, you end up with essentially 2 protons and 2 neutrons, and you form a helium. And that's what's happening in stars. And then a helium could slam into a hydrogen, and what do you make when a helium slams into a hydrogen and it sticks? Look at the periodic table, what do you make? Lithium. And if a lithium slams into a hydrogen and it sticks, we make a beryllium. and so on and so forth. And so atoms or stars start as all hydrogen slamming into each other, making heliums. And eventually when it becomes pretty heavy in helium, then hydrogens will slam into some heliums because that's what's there and it'll make something bigger and bigger. You could even have two heliums slam into each other and make beryllium and skip lithium, right? Any combination of elements can fuse. If they hit each other at the right speed, at the right temperature, they can stick and make a bigger element. And just like in fission, during fusion, some of that matter is destroyed and energy is formed. And I used to know the number, and I think I still remember it. I think inside our star, which is a medium-sized, our sun, which is a medium-sized star, every second, 6 billion kilograms of materials slam into each other and fuse into making bigger elements. And out of that 6 billion kilograms every second, only 5.96 billion remains. So 0.04 billion kilograms of matter is transformed into energy every second. And we know our sun is transforming something into energy because it is a constant source of heat and light. And so fusion is what's happening inside that's allowing that to happen. And so fusion is extremely energetic. It's actually more energetic than fission. And so we do use fission for nuclear power, but scientists have been trying to figure out, could we do fusion on Earth? Because fusion would be so much more efficient. We'd get so much more energy out of fusion than fission. But there's some problems. You need to reach those really, really, really high temperatures. And how can you contain that amount of energy that's being released from a fusion reaction? And actually, going back to nuclear weapons for a second, in the atomic bomb, when that chain reaction is happening, in that split second where it's so much heat and energy that it explodes, it's hot enough for nuclear fusion to happen. Right before it expands, when all the energy is there and is sending it out, that's enough energy for nuclear fusion to happen, but then it expands and cools and that temperature is lost and the energy is gone. So some people say nuclear fusion is our future for energy, but we'll have to wait and see. Any questions on fission or fusion? Yeah. Fusion creates more energy, but it has to happen at really hot temperatures, and we haven't really been able to make that a consistent energy source yet. Fission, energy sources, nuclear power. We're already using fission. Because fission we control by just sending a slow neutron at the uranium-235. And actually, someone in my first period wrote on the chat, and I don't know, I don't pay attention to the latest and greatest of nuclear chem, but they said that some power plants are starting to use thorium instead of uranium-235 because it's safer and easier to control, which just makes people feel even more comfortable about nuclear power. So I'm not sure if that's true, but he seemed pretty passionate about it, so I'm guessing it is. Did they mention it in the video? I didn't watch the video this year. Fail on my part. So I do want to remind everybody that tomorrow is an on-demand day, and on-demand days in science sometimes are makeup days, but the next 3 Wednesdays you do have an assignment to do, and it goes in the test category. So tomorrow is the first of the 3 Wednesdays, and you're supposed to be researching a nuclear topic. And remember, the information is already all in Classroom. You could do your research tomorrow if you'd like. The research is technically due next Wednesday, but you could turn it in tomorrow. And for 10 points is for the research, and then 10 points is for your Flipgrid video. And again, technically I assigned it over 3 Wednesdays, but it's all there. So if you just want to do that assignment and get it completely done tomorrow so that you're good with those 20 points of test points, you're welcome to do so, but just know that you do have an assignment to be doing in class tomorrow. All right.